This is the ordinary differential equations to be solved. Okay, so our given equation here is the second derivative of y with respect to x plus 3dy over dx plus y equal to 0. So by Taylor series approximation, so we have this if prime of x is approximately equal to this one, and we have the second derivative of y with respect to x is approximated by this Taylor series approximations. So by substitution here, okay, so by substitution here, substitute the Taylor series approximation in our given differential equation here. So we have this, and we let f of x equal to y sub I, f of x plus h equal to y sub I plus 1, and f of x minus h equal to y sub I minus 1. So by substitution here, we have this by substitution equal to 0. So by grouping like terms like this one, so we have also this one. Now we have the step size equal to 0.01 here. So we have this by simplifications. Okay. And now for I equal to 2, here we substitute here, I equal to 2 here. So we have y sub 1 minus 1.999 y sub 2 plus 1.015 y sub 3 equal to 0. Now for I equal to 3 here, so we have the new equation here, y sub 2 0.985 y sub 2 1.999 y sub 3 plus 1.015 y sub 4 equal to 0. So if we continue this pattern up to y sub 101, we have the last equation here. So this is our last equations. Our boundary condition are y sub 1 equals to 3 and y sub 101 equals to 20. So our first and last equations are respectively this one. So this is our first equations, and our last equation is this one. Okay. So our step size here is h equal to 10 minus 1 all over 101 minus 1 equal to 0.01. So here, so our step size here is equal to 0.01 here. Okay. So from 0 to 10, and so that corresponds to 1 to 101. So we have to plot this. All right. So this is our representation for our boundary conditions. Y1 equal to 3 and y sub 101 equal to 100. Y101 equal to 20. Okay, so let's generate equations from y. So by using this one, so by using this, okay, so by using this one, let's generate the equation from 0.985 y sub 1 to the last equation here. So from these equations, y sub 1 to y sub 2 to the last equation here is 0.985 sub 99 to y 101. Okay, so this is now our equations by using this by using the Mathematica here. So similar to the metric equations, we can express the system of linear equations above in terms of matrix shown below. Notice the boundary condition y sub 1 equal to 1 and y21 equal to 5 in the example below. So this is our just example. Now before we proceed further, let us have first some examples of our coding here. For example, a equal to this one. So this is our a. So what is the output here? So initialize 2 by 2 matrix here. Set the first element to 1 output the modified matrix here. Okay. So we have another example here. So our example for the A bracket 1 1 here. So normal A. Okay. So convert back to normal list format. Okay. So our first element here is equal to 1. So denoted by this. Okay. Now we have the constant array here, meaning you have the 3 0 0 here. Okay. You have the 3 0 0 here. And for our another example here is two print iterations. Okay, so this is the output for the two print iterations. And we have the two print I equal to I here from 1 to 10. Difference of 2 here. For example, 1, 3, 1 plus 1, 1 plus 2 equal to 3, 3 plus 2 equal to 5 here. Then we have another example here of 2, right? So I equal to I and G equal to G here. So I is 1 to 3 and G here is 1 to 2. Okay. So we have another example here for so sum from 1 to 100 is equal to 5050. Okay, so let's now proceed to our example here, to our problem here. So our number of equation here is equal to 101. Okay. And we have the constant array here. So the constant array is 101 and 101 here equations. So you have the 101 as 0 here. So fill the first row for boundary condition. Y sub 1 equals to 3. So this is our first element in our system of equations here. In our system of equation, 101 equation, our last row here is y 101 equal to 20 here. So fill the coefficient matrix for the system of equation here. Okay. And define the column matrix y, unknown variable y sub 1 to y 101 here. So we have this. Okay. So we have the constant array here. So how many zeros do we have here? And that is equal to 101. Set the boundary condition values here. So that is equal to 3. Y sub 1, 3 is equal to 3. And y sub 101 is equal to 20 here. So display the system in matrix form here. So we have here. So it is similar to this. All right, this one. Okay. So we have the matrix times the first vector matrix here, couple here. So we have here the y sub 1 up to 101 here. So up to 101, and that is equal to equal to 0. So the first boundary condition here, y sub 1 is equal to 3 here. So we have this. So this is our first boundary conditions, and the last boundary condition here is equal to 20 here. So this is our last boundary conditions. Y sub 101 is equal to 20 here. Okay, so let's write all the equations here. So this is our y sub 1 here, y sub 0 here, first boundary conditions, and we have the last boundary condition here is 20. This is y sub 101. Now let us solve these equations, so we have the solution here. For example, here the solution is uh, y sub 1 equal to 3.56199, and y 99 is 20.0521. Okay, so the y sub 1 y sub 0 is already given, and y sub 101 is also given here. So we start with the y sub 1 here. Hello, we have here we start with y sub 1, and our y sub 1 here is 3.56199. Okay, and our y sub 100. So our y sub 0 here is the first boundary condition. Y sub 0 here is uh, y sub 0 equal to 3 here. All right. So this is not included in our equations here. And y sub 101 is equal to 20. Is equal to 20. But they are not included in our equation here because they are the first and last boundary conditions. Okay, so let us use let's plot here. So let's plot all the points here. So what we have here is this uh, curve. Okay. So solving the differential equation by Mathematica here. So we have also this one. Okay, so we have the solution here of the differential equations according to Mathematica. Now this is the numerical solution. So it looks like this. This is the approximate solution by Taylor series and finite difference method. Okay, so they look alike. So they are almost the same. So let us plot all the data points here. Okay, so now this time let's have the points here, the equations. So the corresponding equations is this is our corresponding equations. By plotting all the points, so we have the corresponding equations here. So if you plot the corresponding equations here, so it's almost the same here also. All right. So okay. So the solution of the differential equation is given by this. Given by this equation. So this is our equation. So this is y equal to this one. Now for example, if we have only we consider only 20 points. Here we consider 100 points here. We consider 101 points. Now, how about if we consider only 20 points here? For example, here we have 20 points here. So like this one, so we have the 20 points here. And so the data for our 20 points are, let's write all of those 20 points. So we have the quadratic fit and the cubic fit here. Okay. Now let's graph the quadratic fit here. Okay, so this is a quadratic fit here. So it looks like our original solution here. It looks like the solution by Mathematica, like this one. So this is a solution by Mathematica. So by using the quadratic fit equations here, like this one, so we have also we have almost the same equations here. And for the line plot here, so approximation, because we have only 20 points here. Now we have, for example, in our first problem, we have this equation equal to 0. How about if this is equal to 40? Okay. So if that is equal to 40, we have the solution here. Okay. And it looks like this. Okay. So let us solve the solution here. This now the next example here is the examples of solution of system linear equations. Okay. Because before we proceed to the solution of the problem, let us have first uh, examples. For example, examples of solution of system of linear equations. Our equation here is y sub 1 plus y sub 2 equal to 5. And we have the y sub 1 plus y sub 2 is equal to 3. Okay, so for example, here we solve the system of linear equation y sub 1 plus y sub 2 is equal to 5, and 2y1 minus y sub 2 equal to 3. So the solution here is y sub 1 equal to 8 over 3 and y sub 2 equal to 7 over 3. So we can also solve this using the other way here, the other command here. For example, subscript here y sub 1 plus y sub 2 here is equal to 5. So 2 times y sub 1 here, it's like 2 times y sub 1 minus 2 times minus y sub 2 equal to 3. Okay, so we have the boundary condition, so no additional condition in this example. So the solution here is solve flatten at joints, no equation boundary conditions. So we have the subscript yn, and n here is equal to n is from 1 to 2 here. So display the equations here, the solutions. So we have the solution here. So it's the same here. So we have the solution here. So we have also the same solution here. Okay. Now we have the example of the list of the joint here. For example, list 1 equal to EPC, list 2 equal to DEF, joint list 1 and list 2 here. So we have the output here. So we have another example here of the nested list A, B, C, D, and E, F. So the flattened nested list here is to join all the elements here, E, B, C, D, E, F. Okay. Then we have another example here. So we have equations here, x plus y equal to 3, x minus y equal to 1. So the boundary condition here, the extra condition here. So flatten and join. Flatten and joins equation boundary condition here, x plus y equal to 3, x minus y equal to 1. All right, so let's now solve our equation here. So our new equation here is it is now equal to negative 40.0 here. So this is our new equations to be solved. Okay, so this is equal to, actually this is equal to negative 40 here. So if that is negative 40, if we use the find difference method here, we have this expressions, this one. Okay, so number of equation here is equal to 101 here. Okay, then the boundary condition here is y sub 0 here is equal to 3, and y sub 101 is equal to 20 here. So solve the system equation here from 1 to 101 here, or just like our equation is only we have only 100 equations. So 1 to 100 equations. So the y sub 0 here is equal to 3, and y sub 101 is equal to uh, 20. Okay. Okay, so this is now our equations. Okay. So these are the system. This is now the system of our equations. This one. Okay, so we have the variables to be solved, y sub 1 up to y sub 100. Y sub 0 and is already equal to 3, and y sub 101 is equal to 20 here. Okay, so we have to reduce this one to find the equations. Okay, so the solution of the equation here is, the solutions are y sub 1 equal to 3.949 up to the last equations. The last variable here is y sub 100 equal to 20.1481. The y101 here is already equal to 20, and the y sub 0 here is equal to 3. Okay, so let's uh, line plot here. Okay, so what we have here is this one. Okay, so if we have also the data, we have also the data here, and let's plot the data here. So the quadratic fit here is uh, the quadratic fit here is 5.83615. So this is the quadratic fit, and this is the cubic fit here. So let's plot the quadratic fit here. Okay, so it looks like what we have here. Okay, and our uh, mathematical solutions looks like this one. So these are our mathematical solutions here. Okay, so these are our mathematical solutions. So uh, they are almost the same. So we have the same graph here, approximately equal, approximately they look alike, like this one. This is the approximate solution by finite difference method, like this one. Okay, so by plotting that using the quadratic fit, so we have also this one. We can also use the cubic fit, no? But for me, the quadratic fit is enough.